In 1983, the international scientific community did something that sounds like a surrender. They officially stopped trying to measure the speed of light. This wasn't because they ran out of curiosity. It happened because they realized this number isn't a variable. It is a fixed limit built into the structure of space. For centuries, the idea of light having a speed at all was hard to grasp. Because vision feels immediate, it was easier to assume light arrived everywhere at the exact same moment it was created. Galileo tried to test this in the 1600s with a simple experiment. Two people stood on distant hilltops with shuttered lanterns. One person uncovers a light, and the second person flashes his own back the instant he sees it. Galileo found no detectable delay. The light was moving too fast for the human reaction time involved in his lanterns and shutters. Galileo's experiment is often called a failure, but it was actually a massive turning point. He stopped treating light as a philosophical mystery and started treating it as a physical quantity that could, in principle, be timed. To find the first real proof that light takes time to travel, astronomers had to look far beyond Earth. In 1676, Danish astronomer Ole Romer focused his telescope on Jupiter and its moon, Io. Io orbits Jupiter like a reliable celestial clock, disappearing into the planet's shadow at predictable intervals. But Romer noticed the clock was drifting. At certain times of the year, Io's eclipses occurred later than they should. Romer realized the moon wasn't slowing down. Earth was moving away. When Earth was on the far side of its orbit, the light from Jupiter simply had farther to go to reach his telescope. This was the conceptual victory science needed. By measuring that delay across the solar system, Romer proved that light does not arrive instantly. By the 1800s, physicists wanted to stop relying on the orbits of moons and capture light in a laboratory setting. In 1849, Hippolyte Fizeau set up a round-trip path for light across 17 kilometers of the Paris countryside. He used a rapidly spinning toothed wheel to chop a beam of light into pulses. The light would pass through one gap, travel to a distant mirror, and bounce back toward the wheel. If the wheel spun at just the right speed, the returning light would hit a tooth and be blocked. But if he spun it faster, the pulse could slip through the very next gap. By knowing the wheel's speed, Fizeau calculated the time it took for light to make the trip. Foucault soon refined this by using rotating mirrors. This allowed him to measure the speed of light through water, where he discovered it moved significantly slower than it did through air. This discovery mattered because different theories of light predicted different results in water. By showing it slowed down, Foucault helped confirm that light behaved like a wave. In the mid-1800s, James Clerk Maxwell connected light to electricity and magnetism. He realized that electromagnetic waves traveled at a speed that matched the measurements for light exactly. This meant the speed of light wasn't just a number to be measured. It was a fundamental constant woven into the laws of electromagnetism. Later, Albert A. Michelson used even more precise instruments to look for the ether, an invisible medium that scientists thought light needed to travel through, like sound travels through air. But he found something that defied common sense. No matter which way Earth was moving through space, the speed of light remained the same. It didn't pick up extra speed as Earth moved toward it, and it didn't slow down as Earth moved away. This result left physics in a crisis. Albert Einstein solved it with a radical logical bridge. If the speed of light never changes, then time and distance must. To keep light's speed constant, time has to slow down and space has to contract for objects in motion. This insight became the foundation of special relativity. By the 20th century, scientists were using lasers and cavity resonators to reach a level of precision that was once unthinkable. They finally settled on a value, exactly 299,792,458 meters per second. But here, they hit a wall. Their timing was so accurate that the uncertainty in their results wasn't coming from the light, it was coming from the meter sticks they used to define distance. In 1983, the world flipped the definition. Instead of measuring light based on a meter, we defined the meter based on light. Today, a meter is the distance light travels in a vacuum in a tiny fraction of a second. We stopped chasing the number and turned it into the anchor for how we measure our world.